Thank you everyone for coming. Today we have our third presentation. So we already had a presentation about deploying models with SageMaker, and last week we also talked about customer segmentation. And today we are going to talk about an application of Siamese neural networks about detecting fraud detection with triplet loss. Also, we have a different type of event on Friday, which we have at noon, which is more like a discussion than a technical presentation. We already had one last week when we talked about roles in a data science team. This week we will talk about processes for machine learning project, and then we will talk about building data science teams, and then how to stand out as a candidate in the recruitment process. If you haven't joined yet Data Talks Club, you can do that by going to datatalks.club and filling in the form, and then you'll get a link in your email. For questions today, we'll use Slido. I'll copy a link now, and Artemii will now start his presentation. So Artemii just graduated from Technical University of Munich, and he already has 3 years of experience using deep learning and computer vision. Artemii, you can start. The floor is yours. And I've posted the link to Slido to chat. So whenever you have questions, please open Slido and put your questions there.
Hi, everyone. Can you hear me now?
Yes.
Yeah, nice. So, yeah, let's start with fighting fraud with triplet loss. So, yeah, my name is Artemii. I'm TUM graduate, as Alexei said. Have a big experience in deep learning, in computer vision, and now this was my last project, and I would like to tell you a little bit about it, a little bit about techniques and the problem itself. So let's go. We will start, of course, with the problem, with fraud in ads. We also talk about Siamese network with triplet loss, of course, as a possible solution, and the hash generation that goes after it. We will talk about process itself, how it works now to identify fraud, and the possible evaluation of our models, our ideas, and so on, and of course conclusion at the end. So let's start with the problem. So one of the big problem of the ads websites is the fraudsters who wants to create a fake listing. The idea behind it that they create a fake listing, the user just try to buy something from this fraudster because of this listing, and then money goes to the fraudster and user have nothing, of course. And fraudsters, to create this fake listing, can generate a new text. They just can write anything, but they need to use existing image. And most often they use the already existing listings that are in this website. So but the problem here is that, of course, there are many different strategies where the website can detect the duplicate listing. So because of it, fraudsters also modify the image and make it different. And also there are a lot of different techniques that can find the modification of the image, but there are a lot of data in this website, and it's too much data to compare. It's like each image with each image, and it's impossible to just do the regular check image to image. And hashing can help us, and existing perceptual hashes are quite good for small changes, as you can see here, with a small rotation, and yeah, perceptual hash can find and check that it's like the same image that was a little bit modified, but it's not good enough for bigger changes. Like here is not only rotate, but also if horizontal flip, change in color, adding noise, and so on. So idea behind this talk is that we need to find a way to generate hashes to find these modifications. And one of the possible ways is the Siamese network with triplet loss. Let's start with embedding. So the embedding is a representation of the high dimensional space into the low dimensional space. And in our case, it's images that have a lot of information inside it. So it's a lot of pixels in the width and a lot of pixels in the heights. And each pixel can have like many layers, like for example, RGB as a most popular one. And yeah, we can just use all these numbers because it's too much, and we want to represent it as a small vector in some small space, and then use these numbers to do all the stuff. And one way of doing this and collect embedding vector is to use Siamese network. So what is the idea behind this triplet loss and Siamese network? For example, we have 3 images. Like here we have a blue one. Sorry, we have a blue one as an original image, a green one as a positive image, or it's a image that was modified and it should be really close to the original image, and negative image, it's some other image that we don't use. Here it's red. And after we train the network, we should have at the end something like this. So the original image and modified image should be close to each other in this vector space, and the red image as not similar, just any other images should be quite far away from these 2 images in this embedding space. And how does it work? So Siamese network with triplet loss, learning with triplets. We have 3 triplets, as similar as the previous example. It's anchor, positive, and negative image for each triplet. And anchor, it's the just original image. Positive is the image that should be close to this original image. In our case, it's modification of the image. And negative, it's the other image that should be far away. And that every part of the triplets as anchor, as positive and negative, goes through the network. And it should be the same network for each image, but this network can be different for different projects. It should be some pre-trained network. It can be the networks that you just create yourself or something different. But the one thing should be here is that it's the same network for each of these examples. At the end, it gives this A, P, N embeddings. So A, of course, for anchor, P for positive, and N for negative. And then we calculate the loss having these embeddings. And this loss calculated in this way. So we have a distance between anchor and positive image, and distance between anchor and negative image. And as we can see here, the distance between anchor and positive should be as small as possible, and anchor and negative should be as big as possible, so we have the lowest loss. Also, we have alpha here, which is quite important because, for example, if we have a situation when we have no alpha, the best solution for our network will be just nullify everything, every weights in our network, and all the anchor, positive and negative example embedding would be also 0. So at the end, loss would be 0, which is like the greatest solution for network, but not the greatest solution for us, because it's like every image shouldn't be the same and shouldn't be like with 0 embeddings. But when we add this alpha, if we nullify all the weights, the loss will be still the alpha. So we have 0 here, and alpha at the end. And it's not the best solution for the network because, for example, there can be solution where anchor and positive are 0 and negative is the 1. So the answer will be alpha minus 1. So of course, the nullifying is not the best option, and alpha helps us here. So yeah, this is how Siamese network with triplet works. The concept behind it works, and there are also quite fun useful tricks here. As I said, it works with triplets, and we need to generate these triplets. But for example, anchor, one positive image and one negative, and the same anchor, the same negative image, and the different positive image, it's two different triplets. So from one image, we can generate many triplets, and it will be different training examples for our case. And the idea behind it, that the Siamese network learned not something from the image itself, but it learned something from transition. And if we generate different transitions, different modification of the image, it will learn these transitions, and this is what we want, not the something behind image itself. But still, here's the problem here. So we will find the transition, but we will not learn what to do with the images that are similar to each other, but actually they're both original one and they're not modified. For example, as here, it's an example of similar but not augmented images, here you can see one example where the main object is the same, but the background is different. And the second example is when the object on the foreground is different. It's different cars, but background is the same. It's quite hard examples for our case, and yeah, usually network will think that it's modified images. So to do something with this example, we can use our different tricks. It's we can choose not only different positive example, but we can choose negative example, not randomly, but try to do something. So let's split our possible negative to three groups, our triplets to three groups. First of them will be easy triplets. Even with the margin added, it's still the distance between anchor and positive plus the margin is less than the negative. It's the semi-hard triplets where distance with the positive is smaller than the distance with the negative, but all of this is smaller than distance with the positive with alpha. And hard triplets, it's triplets where network is really struggles to calculate something. It's when the distance between anchor and negatives is smaller, even smaller when the distance with anchor and positive. And here you can see the example of this semi-hard triplets, semi-hard negative here. So we have the same image but different background. It was in the previous slide. And yeah, with some positive, it will be really easy to understand this, but to differentiate this, but with adding the margin, it would be not so hard. It will be harder. But here the other example is for the hard triplets. The images are really the same, and if we use some modification, it would have much bigger distance than these two negative examples. And to do something with it, we can evaluate several random batches of triplets. So we can find the triplets with the highest loss, and then we can train these triplets with addition of the random triplets. So this makes us not only train on the hardest examples, but also add some random in it and not to overfit this like highest loss. So yeah, we understand how the Siamese network works, and here this is how we can use it in the to generate a hash. So we have embedding, and now we can translate it to hash, because hashes are important to use in the big databases to make everything faster. Everything works much faster, as I said just. The one simple method to generate embedding from the hash, to generate hash from embedding, is local sensitivity hashing with random projections, and it works quite simple. So we have different objects in our space, then we project it to some vector, some random vector, and then we check whether this projections is more than 0 or less than 0. And if it's more than 0, we have this hash as 1, and if it's less than 0, we have this hash as 0. And we can use as much as random vectors as we want. And the idea behind this is that the embeddings that are close in its space will be close in the new space, as you can see in this simple example. And yeah, while I did my project, it's quite interesting that with using LSH with random projections, it can show the huge drop of the results at small hashes. For example, if we use only 64 bits of hashes, there will be quite big drop of any results comparing to embeddings, but almost the same results at big hashes, like drop for less than 1% when we have like 512 bits for one embedding vector. So yeah, now we understand how the process from the images to hashes works, and we need to understand how it helps to fight the fraudsters. And let's start from the process behind the identifying the fraud itself. First of all, the image goes into the system, and then system tries to find the closest image to the image that we uploaded, and it also calculates the distance of this between this image that we uploaded and the closest image. And there can be three different situations here. First of all, the distance between these images is less than minimal threshold, and this means that these images are really similar to each other, and we just automatically reject uploaded image because it's too similar to other image in our database, and it's clearly the duplicate. The other thing is the distance is more than maximum threshold, and that means that these images, even the closest image, is so much dissimilar that we can say 100% that it's not the duplicate and it's completely new image. But these two are the best options that we have. Usually there is a third option when the image, this distance lays between the minimal threshold and the maximum threshold, and the real person should decide whether it's the duplicate or not. So for example, it can look something like this. So we have the uploaded image, we have the possible candidates with the distances behind them and between them, and the person should find out, the moderator should find out whether this uploaded image is original or duplicate. So then we have this process, and we need to find out how we can understand that our solution works to model this process. And for example, we can use a precision recall technique. So of course we have rejected, we have approved, we have two classes. It can be really easy, but there is a problem that then we need to use like the threshold. To find this problem with threshold, we can use also quite famous rock area under the curve, or Rockaway process that can find different thresholds, and for each thresholds find different like positive, negative answers here. But we have the other problem. It's not a binary task itself, because we also need to find out that the closest image that we found is really the same image as we uploaded. So yeah, we need to modify Rockaway somehow. And here's how we can model the process. So yeah, first of all, we have a database of different images, and we can take some stuff from this. And from this it will be images that will be used as original images. As I said, we have two classes, original and augmented images, and also we have this images that were augmented, and it will be augmented images. Then we mix all these images and so the algorithms will not know which one of them was augmented or not. And then we post it through the system, and we find the closest images, as I said before, in the real process. And if the distance is lower than some threshold, we consider is augmented. So yeah, it's really close to each other. It's not original image. It's should be modified image. And the other option that the distance is bigger than threshold, and then we consider as original. And then we need to evaluate this process. So yeah, there can be 4 actual outcomes. If the distance is small and we think it's the augmentation, we can check, is this closest image is part of augmented image and the closest and unknown are the same images? Then it's true positive. We found our modified image. We found that it's clearly the augmentation, and we were right. The second option, with the distance still small and we think that's augmentation, but it's not the same picture, or it's not the part of the images that were augmented. That means it's false positive. That means that we were wrong and the image is not the modified, it's some original image. And this other thing, if we think the distance is high, and we think that's original, and we check that unknown is not a data set at all, that means it's original images, and we are right, it's true negative, it's not the modified images. And sorry, yeah, and if the distance is still high and we think it's original, but this is the part of originals that were augmented, it's clearly false negative, because we were wrong and we thought that this is original, but it wasn't. So with this modified Rockaway, we can do this process with a lot of different thresholds, and we have the same threshold rules as in regular Rockaway, but we add here an extra condition, and we can also use the top 2, top 5 modifications here. It's the modification where we can where we check not the closest images, but top 2 closest images and top 5 closest image. And whether it's not has all the not have the same statistics meanings as regular Rockaway, it's still a good estimator for different approaches. So we can try different pipelines, we can check which networks works better and so on. So when I tried it, I did some research, and for my task it was like the best option was with VGG16 with 256 bits in hash. And the fun thing here is that also while I did my graph analysis, I found interesting stuff here. For example, as you can see here, it's a graph for modified Rockaway for top 1, top 2, and top 5 positions. For this modified Rockaway. And as we can see here, top 1 is have lower result than top 2 and top 5, but top 2 and top 5 are much closer to each other. That means that if we give to the moderator the option with only one possible candidate, it can be, of course, be easier to moderator to check it, but we have worse results. But when we have decision to give him 2 or 5, we can always choose top 2 result, because it's quite the same as top 5, but for moderators it's much easier to find out whether the image is duplicate from 2 images than from 5 images. So yeah, in the end, we found out that fraudster can cheat by stealing and changing the image of other user to create a fake listing. And we need a fast way to find similar images. So we can find distances between these embeddings. And we can compute this embedding using Siamese network with triplet loss. And we can use different tricks with positive and negative examples. And also we can simulate the process to do different experiments and trying to find the best models. In this way, we can quickly and effectively identify the fraudsters. And yeah, we can find out which algorithm works better here. So yeah, thank you for your attention. Here is my LinkedIn contacts, and you can check it with the QR code also. Thanks.
Yeah, you can post the link to your LinkedIn to our Slack.
Yeah, sure.
Yeah, thank you, Artemii. Have some questions. If you can stop sharing your screen, I'll. So we have a couple of questions. So the first question is, why did you need to do this? I'm not sure I fully understood the problem.
Okay, let's start with the idea.
Do you want to share your screen again, maybe?
Yeah, I think I can talk through
Okay.
this problem. So we have a lot of different website, as for example OLX or eBay, Kleinanzeigen, or different other website where the people post their ads and they want to sell something. For example, I want to sell my phone to other person. I post my phone. I post my listing here, but other person, fraudster, just take my photos of my phone, change the text itself, and then post it with like 100 euros less price. And when the other person who wants to buy this phone come to website and he see two different listings with the same phone, but one of them is much cheaper, and he connect with this person and like just give them all his money. Sorry. Yeah, give him all his money, but have nothing back. It's bad for this person, of course. This is bad for me as a seller because I also can't find anyone who wants to buy from me, and it's bad for the platform because it's like no trust for the platform anymore, both from the seller and from the buyer. So the platform, any platforms wants to check whether the uploaded image with the new listings is already existing one, and this is the image that somebody already posted in the system, or it's a new one, so it's a original listing. So yeah, the problem here is to identify this image, and if this image is modified image, yeah, we can say it's fraudster. If it's a new one, we can say it's okay. Let's think that it's original users who wants to sell something.
Okay, thank you. Then another question we have is, you mentioned perceptive hashes. I don't think I think you mentioned it briefly, but you didn't go into details. And the question is, what are they?
So perceptive hashes is one of the methods that can calculate the hashes out from the image itself. So there are many different ideas behind it. For example, like averaging hashes or yeah, other ones. And the idea behind they use the yeah, they use the distance between the images inside the image itself, between other different regions in the image, between different pixels of the image, and they can generate a hash outside the image. And yeah, it's most popular, one of the most popular methods to generate hashes from the image.
So basically, they require no network, right? While your approach.
It's just mathematical rules, and yeah.
Okay, Saraf is asking, what were the different image augmentations that were used for this project? Why they were chosen in the first place?
So yeah, for the first of all, I wanted not to describe my project. I wanted to describe the idea behind Siamese network and idea behind the possible evaluation of these kinds of working with Siamese network. But in my project, I use crop, rotate, resizing, flips horizontal flips. I also use some image changing of saturation, of brightness, adding some noise, and yeah, I guess this is it.
Okay, thank you. Then another question is, isn't the goal of Siamese networks to learn better representation embeddings?
Um, Yeah, it's the idea of the Siamese network to learn better representation. As I said, in the end of it, we want to represent our image in that way that the close images with like image and its modification are really close in our embedding space than some other image. So that means when we have this embedding and we want to find the closest one, the closest image in this vector space, it should be yeah, the one that was augmented, not the one that was just similar to it. So yeah, you're right.
Yes. Thanks. I think you answered that.
Yeah,
How can such systems be tested, evaluated? How can this be used in practice? So I
yeah.
think you did answer that during the presentation. Maybe this question was asked before, but maybe you can just briefly say in a
Oh,
couple.
okay. The Suraf answered yes in the chat that
Okay, yeah.
was answered.
So skip that. In the loss function, why not removing alpha as well as the max function? Wouldn't
So
that work?
yeah, I guess here I should share the screen.
Okay, let me stop.
So yeah, let's go to the formula. So as I said, just removing alpha, it makes the uh, network just learn to nullify all the weights of the network and have the zero, because zero loss is the best results for zero. So we need this alpha. And the second thing here that we need max, because in the to use how the network works, we use this loss to do back propagation, and usually loss shouldn't be negative, so we cannot use negative loss here. And here we can have this, it can be negative. So this alpha is actually a way to make this distance between anchor and positive and distance between anchor and negative like goes into the negative. Yeah. So to make this yeah, negative, and then adding alpha, we make it positive again. So let me try to rephrase it. So without alpha, we are just cut it at the point where anchor and positive distance between anchor and positive is the same as anchor between the distance between anchor and negative. But when we add alpha, we can like check the situation where distance between anchor and negative is much bigger than distance between anchor and positive. So I hope I answered it. Sorry if it wasn't really understandable.
You can also try to, like, if it's not clear for somebody, we can have a discussion about that in Slack.
Yeah.
Okay, so we answered that. Uh, um, um, how robust are the hashes in the sense that if I calculate the hashes for the same image again, will it be 100% the same? And yeah.
Yeah. Yeah. So when we train everything and we check, for example, I guess this is a question because of the randomness of local sensitivity hashes. And the thing is that while we generate this random random vectors, we can use the same random vectors all this time. So we need to save them and use it for every embedding. So yeah, the randomness here is only on the like the first step of the project, and when we use it, it's not random anymore. So it would be 100% the same.
So you basically generate the hashes once, you save them, and you use them for all the new images, right?
Yeah.
Okay, and then this also there are two questions in one question. So are there other alternatives for hashes?
Yeah, I guess yes. It depends on different tasks. So here, for example, we still can use embedding itself. So, for example, we can use different system to like make things faster. So, as I said, we use hashes here because we want to check whether the image is duplicated or not really fast. And the one alternative is still use like float embeddings, not the binary hashes, and use some systems as FAIS to like make it much faster. But yeah, it should be checked, as I said. It's just a possible pipeline, and yeah, it can be evaluated which one works better and faster. So yeah, there are
And
other alternatives for hashes.
yeah, and I can add that FAIS Insight uses LSH as well. Okay. Does a single threshold work for all settings? How do you optimize the threshold value?
Of course, single threshold does not work for all settings. Here, because of it, here in the evaluation, we use different thresholds to find out which one is like the best solution. And usually, we first of all, we can just check what is more important to us, whether it's to have the chance that more duplicates will go into the system but have less work for moderators, or it's better for us than there is no duplicates go through the system, but there are like a lot of works for moderators. So it can be as logical ideas behind it, just like pure logic, or it can be some statistics methods, like we can check the higher F1 score of it and like just get the result as a like the best threshold. So yeah, there can be a lot of different methods, and this is quite a huge talk, to be honest.
Okay, it seems we have no other questions. You answered all the questions we had. So thank you very much for presenting your project. And yeah,
Yeah, thanks a
thanks.
lot. Thanks for this opportunity.
Yeah. So see you. Goodbye.
Goodbye.